Now we have arrived at chapter 9, in which we want to talk about the deep learning based models for generative modeling of graphs. We have discussed the traditional approaches in the last chapter, and they are very efficient in using them to basically generate synthetic data on graphs that exhibit certain properties that you desire. However, the main drawback about them is that the process is a fixed process and based on handcraft features. Now, the main thing that we are interested in learning how to do about the generative modeling of graphs is how to learn from data. In this case, this means basically training your models on a set of graphs and basically learn how these graphs have been generated. Again, this means you have, for example, a training set including several graphs, and you want to basically observe them and understand their the representation that encodes their underlying characteristics, and then use that to generate graphs that exhibit the same characteristic and basically come from the same distribution and have the same semantic properties. In this chapter, the main introduction to three key elements or three key frameworks for this are included. One of them is the Variational Autoencoders, or VAEs. The other one is the Generative Adversarial Networks, or GAN, with a focus on adversarial approach. And the last one is autoregressive models. In terms of the nature of the work and the concept of autoencoding, these two are more similar to Erdos-Renyi and stochastic block models that was discussed in the previous chapter. And this branch is more similar to the preferential attachment in terms of being autoregressive and the incremental nature of the framework. First, let's talk about variational autoencoders. The goal in variational autoencoder in the context of graph generation is to basically train a probabilistic decoder such that it gives you this distribution from which you can sample realistic graphs, meaning that you can take sample adjacency matrices from this. Now Z here is the latent variable on which you want to condition this distribution. To do so, you have to combine it with a probabilistic encoder model. Let's call it Q. And the idea for the Q is, if you have a graph, it basically encodes it, meaning that it tells you information about this posterior distribution on the latent variable Z. So to sum it up, the first component you need in basically defining a variational autoencoder framework for graph generation is the autoencoder that gives you information on this posterior distribution Z, posterior distribution on the latent variable Z when you have a graph. Generally, what is done is the reparameterization trick, meaning that you assume that Z is coming from a normal distribution, and your network is supposed to learn the mean based on graph and the variance based on graph. So you're basically parameterizing a normal distribution from which you will sample Z. The other component that you would need is the decoder model. And note that these are the parameters of these models that I'm mentioning here. So you want to use p theta to talk about the presence of edges between two nodes, conditioned on the latent variable that you have received. And the third thing you need is a prior distribution over the latent space, which is, roughly speaking, most of the times, the normal with 0 average and 1 standard deviation. Now let's see what kinds of random variables are we dealing with. Per notation of the book, the main thing we are interested in is the decoder, parameterized by theta, which at the end of the day, because we are kind of doing a generative process, we want to interact with the distribution of graphs. So basically, this is the main thing that you are interested in. This is also what's called evidence as well. Now, when you're describing that latent variable z, you're assuming that there is another distribution and the graph, the manifestations of basically instantiations of the graph random variable and this latent variable are basically according to a joint distribution. This again means that if you consider your evidence parameterized by theta, and let's say you're considering the logarithm of this evidence, you can write as follows. You can import your latent variable here, and based on what you know from probability theory, you can marginalize this probability, and this basically is the same thing. Now you can also bring something new here. Let's call it Q, and for now let's ignore that Z conditioned on graph. Let's say this is like another distribution. And what happens here is that this becomes now this. True. Let's import that theta here too. Now, given the fact that logarithm has this shape and is therefore a concave function, you know that this, based on Jensen's inequality, holds. And this becomes your lower bound on the evidence. Now, having that QZ that sort of comes from the encoder and basically reparameterization trick, but let's say you actually have the QZ, consider something like this. Now, if you expand this, what you're going to have is that you're going to have this being this. Now you can see that this becomes your evidence. And this part becomes minus average of this. And this was your elbow. Inspired by all of these, this is the variational loss that the system wants to have, or the objective. So first of all, for each one of the graphs, this holds. So you have the set of graphs, for example, your training set, and then this is what you have. Based on the graph that you have chosen, you have this distribution Q, and you compute this minus this. With this being a prior over Z. So you want this distribution, the encoder distribution that basically gives you the Z, not to deviate too much from this. Therefore, you want to minimize the scale divergence, which is aligned with basically trying to maximize this thing. And this part had to do with your basically lower bound, and you all obviously want to maximize that. So this is the overall objective that you want to work with. If you multiply it by -1, this becomes what is known as elbow loss. The idea is that basically you want even when you're sampling a z from this distribution, you'll be able to generate a meaningful graph, and therefore this component is going to help you achieve that. Now, let's discuss some of the ways in which we can use Variational Autoencoder framework for generative modeling of graphs. The first type we want to talk about is encoding and decoding graphs based on node embeddings. Here the idea is this. Having two node representations, the encoder basically generates the latent node representations, and then the decoder will use these two to determine the probability of an edge existing between the two. This is known as Variational Graph Autoencoder and was first introduced in this work. So here's the idea. First, in order to have the graph, let's say you have the adjacency matrix A and you have features X as input. A is going to be of this domain and X is going to be of this. Now again, discussing the reparameterization trick, you use a graph neural network to generate the mu for that Gaussian distribution for Z, which gives you essentially a mu Z, which is a member of V certain and a certain dimension. Then you have the same thing, so you have another GNN, this time for determining logarithm of variance. Now this is like a practical trick because in order to have like a more stable system, apparently it is better to use this. This means now you can sample a set of latent embeddings such as this. You would have an epsilon and you would have the exp of the logarithms of the variances that you have gathered plus the average. And epsilon is going to come from this domain. And again, this is going to be a member of RVD. Now what we discussed about the decoder was that we wanted to essentially talk about the probability of graph given these latents. Now, given that we're representing the graph with the adjacency matrix, this is what we are interested in, which is the posterior probability of the adjacency matrix given or conditioned on the latent variables. In the original paper, when you're talking about the probability of a node existing between, an edge existing between nodes U and V, given the two latent embeddings of these two, this is essentially how it was formulated. So you would have a nonlinearity, basically sigmoid function, and the dot product of the two embeddings, which is kind of like the simplest thing that you actually can do. Then going down and defining the reconstruction loss, when you're describing this, you can describe it like this. So for any two U and V, this is 2, the probability of this element being 1 given on Z, U, and V, all of these will be multiplied and this will construct this posterior probability for you. Plugging this in, you will get the basically binary cross entropy over the edge probabilities. And when the training is done, basically you can use Bernoulli distribution and basically sample edges. Now the problems with this technique is that first of all, the decoder doesn't have much of a parameter here. Basically it doesn't have any parameters and you're just relying on a simple dot product loss. So this constraint is going to make the representations very limited. And then if you don't have a graph as input, you cannot use this decoder to essentially generate non-trivial graph structures in the output. Now an alternative to node level latents is graph level latents. This time you're going to focus on generating the latent representations for the graphs, meaning that again following that reparameterization trick, you're going to have something like this. You have a pooling operation, and again you have a GNN for mu, and you have adjacency matrix and the representations, and again you this time have the variance for the graph as well. So you have this pooling operation, GNN for sigma, and again the rest of this. Note that the pooling operation is going to take the node representations, as it's going to generate a representation for the graph. Now, having this representation for the decoder part, you basically will have something like this. You will have an MLP, you apply it on this graph representation, and then a nonlinearity, and you get this. This is basically the graph VAE model. And again, here in the creating this estimate of the adjacency matrix, you're again assuming a Bernoulli assumption, and you're using sigmoid as a nonlinearity in order to ensure that it's going to be a valid number. Now again, when you are interested in this probability, meaning the probability of your graph given the latents, for every u and v, what you're going to do is that you're taking this estimate, multiplying it by the actual value plus this. And again, you have something similar to, again, binary cross entropy loss function. Now, discussing the challenges, one is that when you're using the MLP, you're going to have to assume a fixed number of nodes, or you can basically assume a maximum number of nodes and do some sort of a masking approach. You can, for example, look at the empirical distribution of the number of nodes in the graph and then determine this Pn, which basically determines the number of nodes in your graph. And the output of your MLP is supposed to give an A, which is a member of this. And then you can use it alongside n with masking approach to obtain the output. The second challenge has to do with the ordering of nodes. The losses that we've discussed kind of imply that you have to have the same node ordering in determining and in determining the value. And if you don't have that, basically generally this can cause the decoder to kind of overfit to a certain arbitrary ordering of nodes. The first approach to deal with that is that you can apply a graph matching heuristic, and when you're trying to determine this, you can find this ordering accordingly. So again, when you have UV members of V2, you have this specific ordering applied in comparing these two distributions. Now this is still very computationally expensive, and there are some other alternative models that have been proposed. One of them, for example, is to assign an ordering based on using the maximum degree node and doing some sort of a depth first or breadth first search and assigning orders based on those. One other alternative is to have like a set of heuristic orderings, P1 to Pn, and then average the result over those. So all in all, if you want to use this framework without combining it with some of the other things that we will discuss, this is kind of limited to hundreds of nodes because of the computational complexity. Now, VAEs also have their own drawbacks. So these are pretty well motivated from the statistical and probabilistic standpoint, and there are many works that have analyzed the structure of the latent spaces that they have found. However, the main drawback, for example, if you consider things such as images, is that, for example, they saw that it outputs blurry out images and things like that. So GANs do not really require an introduction. They have been pretty successful in other domains such as images and text, and there have been works proposing them for graph neural networks as well. The key idea in GANs is that you have a trainable generator network, G, parameterized on theta, that is supposed to take and generate fake examples. These are going to be the fake examples that it's going to generate, and it will generate them based on a seed that it receives. Then you're going to have a discriminator that takes these fake examples and is supposed to determine whether or not they are genuine or fake. And then the adversarial game and the min-max game that will be used in training. Now let's look at a basic example for graph generation. Let's say you take the z and use a normal multilayer perceptron and you obtain A. And then you use A with Bernoulli distribution and you obtain this. So this becomes your encoding mechanism, and for decoding mechanism you would have a GNN. One immediate advantage over the VAEs is that you don't need to worry about node ordering anymore. So far, when it came to generation, we talked about things such as multilayer perceptron. However, using multilayer perceptron, or basically a simple MLP block, to build the graph or the adjacency matrix has a lot of limitations. And in this section, we're going to talk about the autoregressive versions that actually can be used jointly with the GAN-based methods or VAE-based methods in order to make the results more efficient. In what we discussed before, when you were trying to compute this posterior probability of the graph given latent, for every possible edge, you would take the probability of that being 1, and basically you would multiply everything. Here, what you are assuming because of this multiplication is the independence of each one of the edges from the other edges. However, this independence assumption is very limiting and it's not very compatible with what we know of real-world graphs. Now, in the autoregressive methods, we want to kind of build these edges sequentially. Therefore, this independence assumption is going to be out of the picture. Given that we're going to focus on simple graphs, if you have the adjacency matrix, let's say L is the lower triangle of the adjacency matrix. Again, L is the lower triangular portion of A. It is not the Laplacian. Meaning that if you have Vi and Vj, two basically nodes associated with indices I and index j, it's going to be 0 for any j that is larger than I, and otherwise it's going to be A of Vi Vj. Now the way you want to formulate this posterior probability is going to be like this. Looking at each one of the nodes, you will condition this probability on basically the previous rows of the lower triangular portion of the adjacency matrix. Now the first model that we discuss is called graph RNN, and the idea is to use a hierarchical RNN to model the edge dependencies. So the first RNN is the graph level RNN. This is supposed to capture the state of basically the graph that has been built so far, which means that if you're considering the state of the RNN for graph level, this is RNN graph level, you're going to have the previous hidden state, and then you have L of Vi L. In the original formulation, H0 was set to be 0. This could also be learned by a graph encoder or by learning and sampling basically from the latent space in a VAE encoder and a VAE approach. Now, as you are building this graph, if you're looking at L, you're kind of going down here, talking about the graph level RNN, and then whenever you are at a certain row, you have a node level RNN. This time you would have RNN node. This one will take the hidden state generated by the graph level as its initial, and it's going to basically assume a Bernoulli distribution for the elements in the corresponding row of L, and it's going to sequentially generate them. One key thing to note is that teacher forcing has been used in training both RNNs. Another thing to note is that RNNs learn to also output the end of sequence in order to kind of limit the length of the generated examples. One other important thing to note is that this thing that we discussed here called graph RNN can also be combined with VAE and can be used as the decoder in VAE or generator in GAN. Now, when we're talking about graph RNN, it is worth noting that it has its own limitations. Even though graph RNN is better than, for example, modeling grid-like structures, etc. It has limitations. For example, you will have artifacts such as long chains. And also it's kind of hard to train for large graphs because it requires basically many steps of back propagation. To address this model was proposed, which reads Graph Recurrent Attention Networks. In this work, instead of RNN, GNN is used as in the autoregressive fashion. So when you're looking at this, when you're modeling this probability, meaning this row of the lower triangular portion of the adjacency matrix, is going to be conditioned on the previous rows and related. This is going to be modeled with a GNN, meaning that you're going to have a GNN from Vi1 to Vi minus 1, and you have this. So again, this works on the graph that has been generated so far, meaning prior to row I. So this GNN can be instantiated in many ways. One of the models that was used was graph attention network. And given that we haven't talked about any node features, these could be randomly sampled features, basically just to help distinguishing between the different nodes. Teacher forcing can be used for this training as well. The main advantage of this over the previous method is the fact that if you had the RNN for the graph level, you had to maintain a complex history of the previously generated stuff. But here you're using GNN, and also there have been methodologies such as adding multiple nodes at a time instead of adding one at a time that can help facilitating a better training of this method. Now here is a visual example of how it is being done. Let's say you have the graph that was generated at step t-1, and this is the graph. You could add, for example, multiple nodes at one time. So say you are trying to add node 5 and 6, and these are all of the possible edges. Now what you will do is that you feed it to the grand framework, and then you obtain a probability distribution over the edges. In this case, the line width of the edges that are to be added are associated with the probability distribution from which we want to sample edges. You do the sampling, and then you, for example, find this edge to be added, this edge to be added, and this edge to be added, and essentially update and obtain the graph at the step t. Now let's say we have multiple ways of generating a graph, and let's say we want to quantify how efficient they are. The question is, how exactly can we say which one is better than the other one? Simply focusing on a reconstruction loss is not going to be effective because there's not like a uniform pattern to be expected. In general, this evaluation is a challenging task, and the way it's usually done is to analyze the different statistics of the graphs that are generated, and then you can basically compare the distribution statistics for the generated graphs and the test set. This means, let's say you have a bunch of statistics. So this would be a graph of statistics, for example. And as an example, you can consider, for example, degree distribution. Now, if you have a particular statistics SI, the way you do is that you compute it on the generated graphs and on the test set, and then you will use some sort of a distribution to distribution measure, such as the total variational distance, and then you basically use that to measure the quality of the outputs. The things that are used so far are degree distributions, graphlet counts, and the spectral features. And in terms of methods, total variational score, and then the first Rasmussen distance have been used. Many tasks in the domain of graph generation are focusing on molecule generation. And there are some known properties. For example, you want them to be chemically stable or exhibit certain medicinal properties or solubility.